Alright, so we're going to talk about vectors again, but what we're going to do today is expand our understanding of vectors as two-dimensional objects to a more general three-dimensional object, which is more realistic for everyday world applications because we live in a 3D world. So when we talk about vectors in space, we're not talking about outer space. We're talking about a three-dimensional space we define with our three axes, the x, y, and z axis. So we imagine taking our xy plane and turning it down and shooting up another axis gives us our three-dimensional space. So we have, instead of ordered pairs, we have ordered triples, so x, y, and z. And the ordered part is important, so the point 3, 2, 1 is not the same as point 1, 2, 3. And if I was to define a vector that goes from the origin to the point x, y, z, and I call that point A, I have the vector OA, which is called a position vector, as it starts at the origin. We can break this again into component forms. We have the same two components that we had before, where I have I and j, and we introduce a third component, which is k. And these are unit vectors along each axis, and they have a length of 1. And so if I was to write our position vector, it would be xi, yj, and zk. So the scalar values of the order triple work in conjunction with our unit vectors. So if we were to look at an example where I'm given point A is 2, 5, 3, and I want to try to sketch the idea of that, it goes out 2, it goes over 5 in the y direction, then it goes up 3 in the z direction. So that vector, now it has depth to it. We're trying to draw it in 2 dimensions. And one way we try to do that sometimes is to draw a box around it. So we try to show that there's some depth to it as we go around these vectors. It's harder to do. It's not that important. And we're going to move away from the geometric interpretation and look more at it in terms of components because it's hard to visualize and draw these in 3 dimensions. So in terms of components for the vector, position vector, OA, it starts at the origin and then it ends at point A. I have I, j, and k, and it's just my ordered pair, or my ordered triple values. So it becomes 2i, 5j, 3k. And if I define another vector B, where I have 5, negative 3, and 5, and I want to write that, I could do so as well, but we define the difference between those, this thing called a displacement vector. So you notice that they're tail to tail, the purple and the blue. So it's not a resultant vector, but something different called a displacement vector. And the way that that's going to work is I start at A and I end at B, and I'm going to then subtract the two. So first I need to write B in terms of component form as such, and then to get the displacement vector AB, I subtract the two values. So 5i minus 2i is 3i, negative 3j minus another 5j is negative 8j, and then 5k minus 3k is 2k. So that is my displacement vector, AB. If I wanted to figure out the magnitude or the length of that vector, it's similar to before where we had our Pythagorean theorem. We now expand that to 3 dimensions, and I just take the square root of the component squared. That value gives me root 77. So that has a length of root 77. The angle is a little bit trickier because we now are going to have multiple angles to define a direction, but we can still do it, and down the road we will. Alright, one of the bigger problems in the first 2 sections is talking about a position vector that's some portion of a way along some displacement vector where I have 2 points. So we'd start as we did before. I want to take a rough sketch of what these things look like, A and B. I'm going to look for that displacement vector AB, and then I'm going to scale that by 30% and then add that to point A. So that's kind of the overview of what we're going to do here. So I find my displacement vector by subtracting A from B, and I get negative 2i minus 8j minus 11k. So that's the whole vector in red, but we only want 30% of that. So I'm going to multiply it by 30%, and I get my value. And then since I'm asked for a position vector, I have that point P, I want to add that to vector A. So I'm going to take vector A, and I'm going to add P to it. So I get vector A plus 0.3 of what we just found. And once I do that, I work it out. There's vector A, and there's 30% of that displacement vector. When I combine the two and group my components, I get 1.4i plus 2.6j minus 2.7k. That is that position vector. So again, starting at the origin, that's 30% of the way along my vector from A.